Hey guys, we're going to the moon. Not this episode, next episode. But in this 11th tutorial series, I want to take this opportunity to cover a number of topics that I haven't covered thus far very well. Some of these are basics of reaction control system in terms of rotation. Also some things about translation. We're going to go over usage of the hover engines. And then I'm also going to describe the other orbital elements and change them in real time using cheat codes that you can actually see what this all looks like. So we're actually looking at the underside of the Delta glider right now, and you can see the three holes arranged in a triangle. Those are actually the thrust chamber for the hover engines. So they're engines in and of themselves. They do not use the same engines that the the main thrust engines use. It's not like a Harrier where you direct the exhaust gases down. These are their own separate engines. It would be like a car having a second engine for moving side to side, so that you could parallel park with a single maneuver, just going sideways for a couple feet and then stopping and you're done. So we're on the ground here at Havana, Cuba, and we're actually on what's called a pad, and we can take off from this pad. I haven't demonstrated the use of the hover engines yet, but there's two ways that you can take off in a Delta glider. You can do the conventional runway takeoff, which is what I've done, or you could take off like a rocket and do a vertical takeoff, and then eventually you would add in some thrust to get going. So the answer is no, I can't turn it off. Even from the external MFD, it will cause a crash. So all you commenters on the internet, can you turn off that beeping sound? It's so annoying. No, I can't. I'll get a crashed desktop. I don't like you, Orbiter 2016. I'll probably never use it again after the tutorial series, unless there's like a major update, like a 2016 P1. Okay, so we need to get the hover engines ready to go. So if I do hover attitude control to auto, what will happen is as we start to go up, it will control the three engines here such that we remain hovering, because our center of mass is about here. So if you turned this engine on, we'd essentially flip upside down. We turn this upside down, we do a barrel roll to the left. And if we turn this engine on, we do a barrel roll to the right. So thrust management through the different engines is important. Now luckily with the Delta glider, it does it automatically for you. We won't need air flight control services because we actually will end up using the RCS. And what we're going to do is we're going to put RCS mode in translation. I'm also going to flip my HUD to the color I like it. Okay, so unfortunately, as things should turn out, they nerfed the hover engines on the Delta glider a little bit, so now you apparently cannot take off from the Earth. That's not going to cause a problem except in my tutorial. You don't have to take off from the Earth. So that's not going to be a very big issue. So instead I moved us to Mercury because, yeah, why not? Lower gravity means we're going to be able to take off much earlier. Also, there's no reason for the red HUD anymore. We're going green. Mercury has no atmosphere, so this will have virtually no effect on us. It's going to be raw lift. Okay, so hover engines. To run them, you're going to activate the horizon level autopilot, which will hold you level with the horizon as you increase your hover thrust, which is extremely important. And so what I'm going to do now is I'm going to increase just enough thrust that we start rising. So with every little increase of thrust, we weigh slightly less and less. Okay, now we've come off the ground. So what happens? You can see we went up and now we're coming down again. Now we're stabilizing. So what I'm actually doing right now is I'm matching the hover engine thrust to the gravity of Mercury right now. So what you got to remember about hover thrust is more hover thrust does not mean you ascend from the surface faster. It means you accelerate away from the surface faster. And less hover thrust does not mean that you go close to the surface faster. It means that you decelerate faster. I know that's a little bit confusing to say, but it's kind of important because, you know, if I increase the thrust a lot, I'm going to continue raising up really high. And then if I suddenly decrease it, right, I'm like, okay, I'm going up, I'm going up, I'm going up. But now suddenly I'm going to start coming down very fast. So it's about that acceleration. You need to add in enough hover thrust so that you know what you're doing. And when you get used to it, you can be, you know, you can do it visually, like what I'm doing now. I have no instruments guiding me through this. That's because I'm experienced with using the hover engines. If you don't know how hover engines work, you can have some issues. That's why we have instruments. Cue the airplane reference. So basically, what we're going to be using hover engines for on the moon is approach and landing. So what we're going to do is we're going to we'll ascend to about 1,000 kilometers. And then I'm going to explain from the inside how to hold 1,000. Did I say 1,000 kilometers? I meant 1,000 meters. We're going to go up to 1 kilometer, and then I'm going to explain how to hold it. So in order to do this, we're going to increase our hover engines, and you're going to be watching the acceleration here. You don't want anything above 1 or 2. We want to do it nice and gradual. See, now you can tell we're coming away from the surface now. Our shadow is decreasing, and the landscape is beginning to drop. Okay, so notice now we've actually picked up a vertical speed. If I decrease hover engines to 0 very rapidly, that is the gravity of Mercury slowing us down now. It's 3.7 meters per second squared. So take notice of that 3.7 meters per second squared. As we start to accelerate, if you see now we're at 18, so it's going to take about 6 seconds to kill off our speed, which is at 20 meters per second. So we're doing a stopping equation, right? I'm going to stop at about 850. I'm going to cut the engines, and we're going to let Mercury's gravity slow us down until we pretty much reach about 1,000 meters. We came close, but we're not quite there. So I'm going to add just a little bit in. And now you can see what we're going to do is we're going to attempt to hold altitude. So here's how you do it. You notice if I bring the acceleration very low, we're still rising. Again, this is our vertical speed or ground speed. It really is the same in this instance. And then you have our acceleration. So we're accelerating a little bit, and we've hit 1,000. So here's what you do. You decrease until you bias a deceleration, and then you watch your speed decrease. Once your speed hits 0, assuming you're stopped, in other words, you're not drifting. If you drift, you'll see it get close to 0 and then start going up again. And that's where you zero out your acceleration. So if you notice, I'm decelerating now, and boom, right there. So what I've just done is increased enough so that we have a very little amount of acceleration. Now you can see we are going up about 1 meter every 3 seconds or so, but as far as we're concerned, we're in a straight hover now. And let me see if I can find our shadow so that we can give you an indication of how high we are. So we're going to be about there. Yeah, we might be a little bit high up to see the shadow right now. That's too bad. Oh, you know what it probably is? I keep forgetting the sun. That's not even realistic. There we go. That's realistic size. The sun is so big that when you're 1,000 meters away, like right here, boom, right there, you actually don't have a shadow because the Delta glider cannot cover up the sun totally at this altitude. Ah, Look at our true airspeed. It's at 4.4, 4.5. We've got an acceleration. So we're accelerating. And look at our altitude, 920. We're coming down. And look, there's our shadow now because we're below the umbral altitude. So what are we going to do? We're going to crash into the surface at about 15 miles an hour, which is going to destroy the craft. So what are you going to do? Down here where it says hover alt VS, you're going to choose VS. That will put on a autopilot to hold a vertical speed of 0 meters per second. In other words, a fancy term for a hover. Now do hold. And here we go. The ship's computer has control. Look at the true airspeed, 0.6. It's our altitude in kilometers, 699.1. We're in a exact hover off the surface right now. Precise hover. Kind of hard to tell without any objects around. But yeah, so this is like the ET craft, you know, that would just kind of hang there. And because we're off the surface, we can put our gear up absolutely no problem. And in fact, this is the configuration that we're going to be in when we're approaching the moon. So I'm just going to put the gear down now by pressing G, and now you can see we'll be ready to land again as soon as we get our...
Radiator deployed.
Sure, we'll go with that as soon as we get our radiator deployed messages. Notice that while we hover, this isn't free. We are losing about 2 kilograms per second. So with having 7,600 in the tank, I can only hover for about 50 minutes. But then we're going to run out of fuel, and once we run out of fuel, this is the main tank, which means we can't run these engines to get into orbit. We'd be screwed. We'd crash into the surface, and then we'd basically bake onto the, 700-degree surface? Sure. So what you're going to do is one of two things. You can do a manual approach, or you can do an automatic approach. So let's demonstrate a manual approach. I'm going to disable the hold autopilot right now. Well, actually, you know what? Let me demonstrate something else. Notice that we're not moving in our altitude, at least hardly any. But we still have a ground speed of 0.08 meters per second. So where's this 1.8 centimeter per second coming from? At some point while we accelerated, our autopilot must have not had us exactly where we want to be. So what's going on now is somehow we've picked up a little bit of residual velocity. So what we need to do is look for our prograde velocity vector, and that's going to tell us what's going on. And I have a feeling that it's probably so low that we can't see it. It's kind of hard to find. When you're approaching at a faster speed, it's a little bit easier, because basically you want to kill the velocity until it's directly under you. But what I'm going to do now is I'm going to add a little bit of translation so that I can demonstrate what I mean. So this is to hold a vertical speed, not a horizontal speed. So if I want to start drifting, I have translation. I can add some forward translation. And now we're starting to accelerate. I would really like to see my prograde velocity vector. I don't know why I can't see it. Okay, well, we can play hardball here. So what we can do is we can open up the retro doors here and keep an eye on our speed.
Nose cone open.
We're going to start adding main engines at the same time we add the hover engines. And there you go. There's your prograde velocity vector. So it's about 2 meters per second now. I'm going to close the retro doors now because I can see it.
Nose cone closed.
Okay, so what's going on? We're in a hover right now, but we're also in a drift. So we're moving across the surface at about 7 miles an hour directly overhead, kind of like a helicopter that's almost hovering but is kind of drifting forward. So what we're going to have to do is we're going to have to kill off this speed. You need to do this to center over a pad. But before I demonstrate how to do that, let's go into a little bit of translation basics, right? So we're in a hover, And what I'm going to do is I'm going to pick a star, and we're going to go towards that star. There you go, Vega. So we want to go towards Vega. If I don't use the main engines and I don't have an atmosphere, I don't care what my orientation is, right? Even though I'm about 1 kilometer above the surface and I'm using my engines, I don't care because there's no atmosphere.
Rotation.
Which means I can rotate as long as I keep myself parallel with the horizon. As soon as if I added pitch, that would be very dangerous, because what it would do is if I pitched up, then it would angle these jets at a diagonal, which means I would be adding some forward component and I would fly backwards. So what I'm doing is I'm rotating to an easy direction. And what I'm going to do now is I'm going to add in some translation. So if I press the number 1 and number 3 keys, or you can twist the joystick, I personally prefer the keyboard for RCS movements because you can be a lot more precise. So if I hold down 1, what that's doing is that's adding in a sideways component. There's another way we can do it too. If I press 9 and removed our forward component, hang on a minute. No, it would be press 8. No, it should be 9. Okay, what's going on here? If I press 9, it's been a while since I've done this. Ah, yes, of course. That's because our prograde velocity vector is right there. So our only real good option is 1 in this case. Boom, there you go. So if the base happened to be directly under Vega, we'd now be traveling this direction at about 1.7 meters per second, and given enough time, the base will slowly drift until it's directly under us. Let me demonstrate one other thing too. You don't have to face the direction in order to... You don't have to face the direction you're moving. Let's pick another star, and we're going to move our prograde velocity vector under that. Yes. Yes. We're going to move our prograde velocity vector underneath the Earth and Moon. Okay, so checklist. Horizon level's on. The hover altitude is on. For 0, we're going to hold 0 meters per second. By the way, this is a lot easier. In the old version of the Delta Glider, you didn't have this autopilot. You had to do it manually. We're going to put the RCS mode on translation. And now what we're going to do is we're going to very cleverly maneuver our velocity vector to the Earth and Moon. So what we're going to do is we're going to use a combination of the 9 and 3 keys. 3 allows us to move it this way, and 9 will allow us to slow down a little bit and then change the direction. So if I press 9, now you can see it swinging out. That's slightly more efficient than just doing 3. Uh-oh. I don't like what I'm seeing. Okay, wait. I don't know why this thing keeps disappearing. So I'm pressing 9 right now. 9 is what I'm holding. And there's the Earth and Moon. So even though we're facing Vega, we're actually drifting towards the Earth and Moon. We're drifting in this direction. So if the base was in this direction, it doesn't matter what the front of your craft is, so long as you know how to kill off your speed. So right now we're only at about 1.1 meters per second. How would I increase this if I wanted to go at, say, 2 meters per second? Just keep on adding in the directional keys. 3 will go a little bit this way, and 9 will go a little bit this way. And you keep zigzagging until you have the speed you want. There you go, 2.1 meters per second. Okay, so I'm going towards the Earth now, and let's say, oh shoot, the base is just about under us now. It's time to stop. So what do you do when it's time to stop? You need to add in the exact opposite keys. So we're adding 9 and 3, which allowed you to move the thrust vector behind you and to the right. So what you need to do now is move it ahead and to the left. So ahead is 6, to the left is 1. So hit 6 and 1, hit whichever one brings the speed down faster until you see it bottom out, and then go for another key. 3, 2, 1, right there, 0.18, and 0.5, 0.5, 0.1, 0. I am precisely stopped over almost my shadow. It's going to be somewhere just under the shadow, but I am precisely stopped over the surface now. Because of the autopilot's inaccuracies, eventually I will pick up a little bit of speed, but we're moving about an inch every 3 seconds. I don't think we're going to have an issue if we descend to the surface now. Okay, so now we're going to try manual. So what I'm going to do is I'm going to disable this hover hover hold vertical speed. So what we do is we're going to decrease our hover thrust until we have a nice gentle deceleration. We'll say 0.2 meters per second squared. So right there. So we're accelerating now at 0.2 meters per second squared, about 0.25. And you can see our true airspeed now is picking up. So we're now descending at about 10 feet per second. And, you know, now it's 4 meters per second, 5 meters per second. And you can see very quickly we're starting to approach the surface. So that's comfortable. I don't need to go any faster. So now I'm going to start adding hover thrust again. We're going to bring this to 0. And now we're descending towards the surface at a constant 7 meters per second. So pretty soon we're going to get the GPWS call out for 500.
500.
And we're going to continue going down. And now you can see the shadow. The shadow really helps for determining exactly where you are. You will also have buildings around you if you decide to land at a
400.
base, like on the moon. And when we get below 300, I'm not going to be comfortable doing 7 meters per second. So what are we going to do? We're going to increase hover thrust until we bring about negative 0.2 meters per second squared acceleration until we get to about 4, right? So we're now 6, 5, 4, right about there. So now, done. Kill off your vertical acceleration, and now we're going down at about 4 meters per second. So you can probably see this is pretty close to docking now. And we use a very similar MFD for that. It's actually the VOR VTOL. And you need a radio signal in order for this to work. Now I'm uncomfortable again, so I'm going to increase the hover thrust again. We're going to accelerate it or decelerate at negative 0.15. And we're going to come to within, let's see, we're at 70, 60.
Rotation. Translation.
Yeah, keep it on translation. Yeah, we're getting
50.
pretty close now. So I want to get really slow. We're going to say about
40.
1 meter per second. And now the faster you can do this process and the closer, I think Scott Manley
30.
calls it something like the suicide burn. The closer you get to the surface and before you start slowing down, the less fuel you'll waste.
20.
So I'm below 20 now, so I really don't want to be above 1 meter per second. And you can see now how I'm adjusting the speed to keep it under 1. We're
10.
about 80 centimeters per second. We're below 10. Now I want to decelerate to about 0.2. 0.2 centimeters per second is a really good contact speed. Another thing too you want to check is your horizontal speed, but given that we're below 14 centimeters per second, that's less than a horizontal speed of 1 foot per second, so we're okay. So we're decelerating now at about 0.2, and we're slowly coming down to the surface. About 2.5 is where our wheels are going to touch, and we're getting really close to that now. So just keep it right there. 0.2 and 0 meters per second squared is exactly what you want. Right there. You see when we hit 2.6, we stopped. Acceleration is 0. We've landed. Remove your thrust. Disable horizon level. And just tap the brakes in case we rolled a little bit. And that's it. We're now stopped on the surface of Mercury once again. This is exactly how Neil Armstrong did it. Instead of the this acceleration value here, that he was watching, they had a contact light, and the contact light told them when they touched the surface. So as soon as they received the contact light, they removed the hover thrust, and that allowed all however many tons the spacecraft was to settle onto the surface. Remember, if I have some hover thrust, not enough to lift off, that means I'm lighter. Keep in mind, it's like a variable weather balloon. The higher hover thrust, the more helium I have in the tank. At some point I'm going to start to float. If I keep adding helium to that balloon, we're going to start to float faster. If I put tons and tons and tons of helium in, then we're just going to go up super fast. So that's exactly what happens. So now I'm going to go for a very fast takeoff, and we're going to do an automatic approach and land. So let's go full hover thrust. We're going to go up to 2 kilometers. Activate horizon level. Full thrust, we're going up to 2. Don't let that speed get too high. Because remember, because it's gravity, imagine that we've just been thrown up by our hover engines, right? So now we've just reached the top. We're starting to come back down to the surface. So we're going to throw ourselves again and go a little bit higher. So I'm going to repeat this, but this time I'm going to go up to about 80 meters per second, because 45 wasn't enough. And doing integration in my head, that's about how much speed we're going to need to reach about 2 kilometers in altitude. Pretty good. It was only off by about 35, 70, 65 meters. So I'm going to increase it just a little bit, and we're going to actually hit 2,000. So if you want to target a base that you want to land at, you can put a specific altitude in here and tell it to hold. So we're going to hold, I assume that's in kilometers, but we're going to find out. Yeah, so that's in kilometers, this autopilot. I've never used it before, by the way. Okay, so we should... Actually, it's not. It's in meters. So let me disable this, and it wants to go down towards the surface at about that speed. The annoying thing is, this is going to take forever at the rate this is going. So we're going to bring this up to 2 for an approach. Oh, there we go. Just went crazy. Hold. I think orbit was probably be the most useful thing that we could use right now. We really don't need this side though. Okay, and as you can see, what this is going to do is this is going to stop us at exactly 2 kilometers in a hover. So there are 2 ways we can approach the surface. One is to set our preferred altitude to 2 meters and then allow us to just descend to the surface. That's the really easy way. The slightly harder way is to do vertical speed, which I'm going to demonstrate right now. So we're now hovering 2 kilometers above the surface of Mercury. So what I'm going to do now is go to vertical speed, and we're going to not do that because we're going to go up. We're going to tell it to hold a vertical speed of -30. And part of this is knowing what you need to do, right? You can really screw yourself if you set a value that's too high. There we go. So there's exactly -30. But keep in mind, because our hover engines are only good for about 7 meters per second squared, and the fact that Mercury accounts for 3.5 of it, for every second it's going to take about 3 meters per second to slow down. So if we're at 30 meters per second,
1,000.
we're going to need about 10 seconds to slow down. And remember, it's 1/2 AT squared, which is 1/2 of 3 times, which is 1.5 times t squared, which is 100. So we need 150 meters per
500.
second. So right there now, I'm going to start
400.
Okay. So yeah, this is where you start to get...
300.
Okay. We're going to
200.
screw ourselves. So
100. 50.
Oh,
30,
dear God.
20. 10.
yeah, okay, there you go. So I highly suggest not doing that. Did we get a gear collapse? No, we didn't. I can't believe that. Does the gear... Yeah, the gear actually works.
Radiator deployed.
I can't believe that. Well, we really lucked out on that one, I tell you. So here's what happened. I got confused between up and down. I was explaining we needed to go down, but I thought down was towards 0. It's really up. So what we needed to do was this. So I highly suggest not doing that because you can really screw yourself with that. But I like getting things right, so we're going to try it again. Below 1 kilometer, we can do 20.
1,000.
So know which button you're going to hit before it's time. Okay, we're going to go down to 15 now. And remember, at 10 meters per second, it's going to take you 150 to stop. So you want to be below 10 meters per second when below 250 meters above the surface.
500.
I can't believe we didn't get a gear collapse.
400. 300.
Okay, let's bring in the speed down now to 10. But see, that gives you an example of how you can screw yourself.
200.
If you don't do the math right or you get lost at the last second. Okay, 150 to stop. We're bringing the speed down to 5 now.
100.
Okay, bringing the speed down to 3. And below 50, we'll go to
50.
2. Going to 2.
40.
Below 30, we're going to go to 1.
30.
Going to 1. Below 20, we're going to go to 1/2.
20.
20, going to 1/2. 15, going to 0.4.
10.
10, going to 0.3. So I've demonstrated for you what happens when you don't get on top of this. Going to 0.2, that's contact speed. Waiting for contact. Contacted the surface, and look at that. He's actually reduced the hover thrust. Disable your hold, disable the horizon level autopilot. And we're on the surface again. So again, watch yourself when you start getting close to the surface. You got to do the math and make sure that you can stop again with full hover thrust. As you can see, I went to full hover thrust and I was not fast enough to stop from crashing into the surface. So you really have to watch that when you start getting down close. Now I'm going to just demonstrate the new version of it. So we're going to target 1 kilometer per second, and that's what happens when you forget to hold the horizon level autopilot on. So now what's going to happen is we're going to have a little bit of forward velocity that we're going to have to kill. So let's just wait for us to get to 2 kilometers. And when we reach 2 kilometers, we're going to eliminate this. So I can tell you right away, even though it's safer, I'm not going to use this mode because 20 meters per second is honestly wasting fuel. We're using way too much fuel just to like hang out here when you could do it faster. Remember, every second of hover that you hold on Mercury is about 2 kilograms per second. If you're on a, you know what? I think Mercury is the largest airless world. Yeah, Mercury is the largest airless world. So that's the biggest problem that you're going to have is with either Mercury or Mars. Mars is the kind of question mark region where it's like, do I have enough power to hover or not? It would behoove you to hover because on Mars you need to get about to 800 miles an hour just to do your takeoff. Okay, we're coming up on 2 kilometers now, so the autopilot is beginning to slowly throttle things down as we approach. And we'll enter into a stable hover once we reach that altitude. And then at that point, we'll see what our true airspeed ended up being. See? Nice and safe. We can do that to get to the surface. One really nice thing is the more advanced aircraft or spacecraft like the XR2 Ravenstar, you can just press one button and the entire landing sequence will occur. Oh yeah, and it'll also disable itself once it lands. Okay, so we've stopped now, and you can see we've still got a true airspeed, so we got to find our prograde velocity vector. We've got speed somewhere, and we've got to kill it off. Okay, I cannot find it. Notice that we're still holding Vega. That's a pretty good indication of how powerful this autopilot is. Okay, so what you need to do now is you need to play around with the translation. Start hitting keys and see what reduces. You can hit 1, 3, 6, and 9. Don't hit 2 and 8. What 2 and 8 will do is they will actually fight your hover engines. On asteroids, your translation is actually powerful enough to be your hover engine. But if you notice, what I'm going to do is I'm going to increase translation, and as a result, you'll see a decrease in hover engine thrust. And I'm going to add some downward translation, and that will fight the hover engines, and you'll see an increase in hover engine thrust. See? So that's not good. Don't do that. Alright, so let's try pressing 1. 1 goes up, so we're going to press 3. Okay, 3 went down and then went up again. So it's between 6 and 9. It's 9. 3. Again, start playing. I'm playing with 1 and 3. Now I'm going to play with 6 and 9. And 1 and 3 again. And 6 and 9 again. You can't stop completely. You can get pretty slow. 6, 5. Okay, that's good enough. Okay, so now how do you get to the surface? Really easy. Just decrease this as you would expect. We're going to do this all the way down to about 2. Actually, let's do 3 because we actually do contact at 2.5. So let's see how good it is with this. Again, I consider this wasteful. There's no reason why you need to be approaching the surface at this slow speed. So if you want to increase the speed, you can temporarily disable it, cut your hover thrust, let yourself accelerate. But again, watch yourself, don't go too fast. See, now that just got rid of a lot of time that we would have wasted. So we're going to watch that 20 start coming down pretty soon. If it doesn't, then you would know that the behavior of the autopilot isn't working properly.
500.
Okay, we're starting to get pretty close.
400. 300.
Is it going to stop?
200.
Okay, there it goes. So it's good. It's good for when you get close to the
100.
surface. But when you're far away, it stinks because you don't want to be holding 20 meters per second.
50.
You're just going to waste time hovering.
40. 30.
Oh yeah, this is real fast. It's really good when you get close to the surface, but it sucks when you're high up. Wow, this is probably even faster than I did last time. That's good. It's a good autopilot. It's about 2 meters now. Oh, we just blew 3. I wonder if it's smart enough to know that I want to land. Okay, now that we're below 3, let's just go ahead and disable this. And just decrease it a bit. There you go. Just tap it, or you can screw yourself. Disable horizon level autopilot, and that's it. So that pretty much wraps up how to translate and use hover thrust. The next thing that I wanted to talk about was, I think, a little bit of advanced rotation topics here. So what we're going to do is we're going to go back to Earth. Okay, so one of the main reasons I want to talk about rotation is because I feel like I went over it very quickly.
Rotation.
For some of my other orbiter videos, and I want to be a little bit more clear about what's going on here.
Radiator retracted.
Okay, so you're in space. You can't see mainly what's going on, but when I add rotation, it's going to activate thrusters in pairs. So if I press 1, what that's doing is that's twisting us so that we turn to the left. So you notice how Newton's third law, the plume is upwards on the front and it's downwards on the back from what you can see. And now if I add the opposite, you can see that. So it's action to reaction. And you have to do opposite thruster pairs. If you change RCS modes to translation, now you see it's same side pairs. And that doesn't rotate us, but what it does do is that changes, rotation. Where we are. So it's precisely paired so that we turn about our center of mass. Now with the pitch thrusters, we're going to get 2 up or 2 down. There don't need to be any pitch thrusters on the back. So there's only a single pair and they don't alternate for pitch. The next thing is roll, and these guys do alternate. So you can see there's one on top of the wing and there's one underneath the wing. And then again, if I start adding the opposite roll, you'll see that effect. So real quick, pressing the 2 key will pitch you up to your relative orientation. Pressing the 8 key will cancel your pitch. If I keep pressing it, you will go down. You will pitch down. And if I add 2, we'll cancel the pitch down. If I start adding some 4, then I will begin rolling left. And I will continue rolling left until I hold the 6 button, which will roll us right. And if I release it, we'll stop. If I keep holding it, we will begin rolling right. If I press 5, that will kill all rotation. Nice cheap. Okay. Now if I press 1, that will twist us to the left. And if I hold 3, that will cancel that twist. If I continue holding 3, I will begin twisting to the right. So that's how rotation works. Okay, So now I'm going to talk about the classical orbital elements. So what are the classical orbital elements? There are 6 orbital elements which describe any orbit. Any single orbit that I can have needs 6 plus the center body. So you need the planet, which doesn't count as a classical orbital element. You need the semimajor axis, the eccentricity, the inclination, the longitude of the ascending node, the argument of perigee, and the true anomaly, or the true longitude. Basically, some of those should sound familiar because I've used some of them in my demos. So let's change this frame. There we go, so that you can see it better. So let's start going down by down, or one by one. What is the planetary body in the center of the orbit? It's whichever planet or moon or star accounts for the majority of the gravity field. In this case, it's the Earth, because if you look, the gravity field is 1.00. It's not Venus, because if you look at Venus, it says 0.00. To do auto-reference, it'll tell you what you are. Now, you can have valid orbital elements, like, for example, the first one down. Oops. There we go. The first number down, that's your semimajor axis. We have a valid semimajor axis for every planet, moon, and star in the sky. If I do Venus, that's our semimajor axis for Venus right now. It's perfectly legitimate, but it's probably not a good idea to follow it because Venus is accounting for less than 1% of the gravity right now. And as you can see, it's wildly changing. To do auto-reference, we go back to Earth now. Put the frame. There we go, mod. I never remember those things. So you won't be able to see the cheats that I'm doing now, but basically what I'm going to do is I'm going to start manipulating every single one of these in the scenario editor. So what is the semimajor axis? It relates to the energy of the orbit. Interestingly enough, the energy of an orbit is considered negative until you overcome the escape velocity. So the smaller the semimajor axis gets, the more negative it becomes, or the more negative the energy becomes. The larger the semimajor axis gets, the more towards positive the energy becomes. And then when your semimajor axis is negative, you have a hyperbolic orbit. So what is the semimajor axis? It is 1/2 of the distance between perigee and apogee. So if I turn the frame off here, oh my god, mod. Okay. You see the hollow circle here is your apogee, the filled circle here is your perigee. Take this distance here, and divide by 2, and that gives you your semimajor axis. So we can actually find this out right now. We know the Earth's average radius is about 6,371 kilometers. So if I add 6,371, and I have to add that twice. So now we've got the diameter of the Earth. Now we need to add the apoapsis altitude, which is 375. And now we have to add the periapsis altitude, which is 270. And we get 13,387. That's your major axis. To get the semimajor axis, you divide by 2. And I get 6693.5. And if you look, 6694. It's 100% correct. It's only rounded. So that's a quick and dirty way of finding your semimajor axis. It refers to the size of the orbit, right? The green circle on the orbit MFD represents our orbit. The gray circle represents the Earth, which means if I muck with the semimajor axis, What it's going to do is only change the size of the orbit with respect to the Earth. If I change the semi-major axis from 6672 to 16672, the only thing that you see from your perspective is the Earth shrinking. If I do it again to 16672, again, the only thing that changes is we're further away from the Earth. So if I pull these back again, so we're at 6672, or 669, yeah, 6692 is what I meant to say. There we go, we're back in low Earth orbit again. Be careful what you do. If you set it to something like 5,000 and your eccentricity is very low, there's going to be a problem. So what's your eccentricity? It's the difference between apogee and perigee. And it's easily manipulated by running your engines in the prograde velocity vector or the retrograde velocity vector. Right now, our eccentricity is 0.0077, which is a very low value. But if I start to increase it, our semi-major axis won't change. The egg shape of the orbit will change. Our apogee will get higher and our perigee will get lower. You have to be careful about this because if I set it too high, our apogee will get really far away from the Earth, but our perigee will start going into the Earth. So we have to be really careful about this. Like if I set this up to, let's say 0.05, apply, there you go. So we're going to actually go into the crust of the Earth. So we have to be really careful about setting your orbits if you're going to do these cheat codes. So to demonstrate this, I'm actually going to go higher again. We're going to go back to, we'll go to 96692. So then there's the semi-major axis changed again, right? So let's see what different eccentricity values look like, right? So that is 0. Now if I increase it to 0.1, that's what 0.1 looks like. You can do 0.2. That's what 0.2 looks like. You get the idea? 0.3. The more egg-shaped the orbit is becoming. 0.8. Really steep. So how can you tell what the semi-major axis is if you have apogee and perigee? So the eccentricity, or yeah, if you, I don't know what I'm saying. If you have the semi-major axis, apogee, and perigee, you can actually calculate your eccentricity. What you do is you subtract, you have a fraction. On the top, it's apogee minus perigee, and on the bottom, it's perigee plus apogee. So let's do that equation right now. So right now, we can ignore the 10 to the 6 factor. So we have 167.7 minus 12.97. So on the top of the fraction, we're going to have 154.73. Now let's find the denominator. So we're going to get 12.97 plus 167.7. And we're going to get 180.67 on the bottom. So divide the numerator by the denominator, 154.73 divided by 180.67, and we get 0.8564. And our eccentricity is 0.0 or 0.8. And the reason why this is wrong is because I forgot to account for the Earth's altitude. So we need to do dist and get our radius. There we go. So now if we redid the equation, it would be right. So real quick, 174 minus 19.34. We got 154.63, which is basically the exact same thing. You have to add 19.34 plus 174. You get the bottom is 193, so I do 154.73 divided by, it's like 193 something, and I get 0.8017, and I dropped a bunch of decimal places, but you can see that equation is working out. So that's what eccentricity is. Now, what happens if you break the orbit? Just increase the eccentricity value and see what happens. There's an eccentricity value of 0.9. Notice how it's becoming more egg-shaped. What happens if I give it an eccentricity value of 1? We've just hit escape velocity. We're now unbound from the Earth. And you can see suddenly we're super far away from the Earth. The more I increase this value, the wider the parabola becomes. In fact, we've got a hyperbola. There's an eccentricity value of 2. Here's an eccentricity value of 3. Here's an eccentricity value of 5. And if I increase it, you will get a line. An eccentricity of 5,000. You basically have a line. Now, before we move anywhere real quick, I'm going to reset this so that we don't go floating off into space. There we go. I saved the orbit time. Okay, so the next thing is going to be inclination. Inclination represents your tilt with respect to the planet that you're orbiting. So this is best viewed on the map. So remember, our orbit plane is related to how far north and how far south we go over the Earth. So if you see, with a inclination relative to the Earth's equator, there are two ways to describe inclination. You can do to the equator and you can do to the ecliptic. So you'll notice if I do frame EQU, that's the equatorial, the Earth's equator. Right now, we're at a node. How can you tell? The Earth's equator. We just crossed it. That's how you know we just crossed a ascending node. Now, if we change this up, there it is, to EQU, that's the, hang on a second. Are we at an equinox? We are at an equinox. Okay. I had it backwards. Or did I use frame? Yeah, there we go. That's the ecliptic. Oh no, I had it right. So that's the ecliptic. No, I'm saying it, I have it right, but I'm saying it wrong. That's the equatorial. This is the ecliptic. So the ecliptic is going to be the plane of Earth's orbit around the sun, and it's extremely important when you want to chase planets down. You notice that the difference between the ecliptic, there's a difference between the ecliptic and the equatorial. Let's see what that is real quick. So if you see the inclination is 74.33, and if we subtract it by the this other value, the equator, 51.44, we get a difference of 22.89 degrees. Does that sound familiar? It should. The Earth's axial tilt is 23 degrees with respect to the orbit around the sun. So let's start messing with this, shall we? We're going to change the frame to the equator. So this will represent the three-dimensional, we'll do QU. This will represent the three-dimensional ball of the Earth. And I'm actually going to disable the HUD because it's getting in the way. Watch how the map changes as I vary the inclination. Here's what an inclination of 0 looks like. Whoops, wrong frame. There we go. That's an inclination of 0. So we're going through the equator right now. If I increase the inclination to 10 degrees, now that means I'm going to go up to 10 degrees north and 10 degrees south. If I increase it again to 23 degrees, now I'm going to go up to the Tropic of Cancer and down to the Tropic of Capricorn. If I increase it to 40 degrees, now I'm going to go about as far north as the lower 48, and I'm going to go about as far south as Tasmania. And if we keep increasing it to 55, this is where the International Space Station is, I'll go about as far north as Moscow and about as far south as Stewart Island. Keep increasing it. Here's 70 degrees. Now I'm going as far north as Barrow and Nordkap, and I'm going as far south as I think that's Queen Maud Land in Antarctica. Let's keep increasing it. 88 degrees of inclination. That's a practically polar orbit. We're almost going over the poles. 89.99. We're basically going straight over the poles now, and every part of the Earth is going under us. You notice how the globe, the reference to the globe is changing as we're taking a different slice of the Earth? What happens if we do 91? Are we going to break the game? No, but can you figure out what's going to start happening? We're not going as far north. But you know what's actually happened? We're starting to orbit the Earth backwards. Here's 100 degrees of inclination. Here's 120 degrees of inclination. Here's 150 degrees of inclination. Here's almost 180 degrees of inclination. We're now orbiting exactly backwards of what we were before. I'm not going to do more than 180 because it might break the game. So that is what inclination is. So what's the longitude of the ascending node? Let's give us a nice broad inclination of 60 degrees. The longitude of the ascending node represents where on the Earth you're going to be transiting the equator. Now, keep in mind that the equator is going to rotate under you. So like the ground track, every subsequent pass will be slightly further west of the previous one. So what it really is it's with respect to the stars. So with respect to the stars, whatever star happens to be above, I guess this is pretty close to Tuvalu. Whatever is above Tuvalu would be precisely where we have the longitude of ascending node. So what this is going to do is this is going to perform a twisting motion. Right now it's 0. Right? This is in degrees. So we're going to change it to 20 degrees and watch how it shifts. It shifts about 20 degrees west. You notice the twist to the right? You can see what's going on there. Let's take it at a slower speed. There's 0. There's 5 degrees. There's 10 degrees. There's 20 degrees. See how that twist is going on? 30 degree shift. Let's get a little bit more crazy with it. There's a 60 degree shift. A 90 degree shift. 120 degree shift. 150 degree shift. 180 degree shift. And now I'll do a 270 degree shift. Starting to look familiar? If I do 0 again, or if I do 359, we should end up exactly where we were. Yep, right over to Tuvalu. Okay, so the next thing is the longitude of periapsis. So what we're going to do now is we're going to change the frame of reference again. I always forget my buttons. There we go. We're going to give us a little inclination here of about, let's say, 0.2 degrees. Finally, healthy orbit. So right now, we're about 90 degrees from where we're going to make our lowest pass. So right now, we're going to say that our lowest pass occurs in the southern hemisphere, because this is the descending node. Actually, this is the ascending node. This is the descending node. Hang on, what's our inclination? Oh yeah, it's about 60 degrees. Let's see which way we're going. Yeah, so this is our descending node. This is our ascending node. So we're going to make our lowest pass in the southern hemisphere, right around the southern Indian Ocean. It's like an isle. It's like the Isle St. Peter or something. It's some French island that's down there. Might be Isle Ilchester, something like that. Anyway, so now we're going to start messing with the next thing. This is the longitude of periapsis. What this determines is where the lowest point in the orbit occurs. So right now, it's in the Indian Ocean. If I twisted it 90 degrees, you will see the orbit on this twist. You'll see the periapsis now move to kind of the lower right side of the Earth, and our lowest point will rotate to being about where Tuvalu is. So right now our longitude of periapsis is actually 235 degrees as it is. So if I change that by 90 degrees, we go to 325, we should see exactly that effect. And there you go. Change it again by 90 degrees, and now we'll have a 45 degree. And now you can see we're actually at the highest point of the orbit. The lowest part is going to be near Vancouver. And if I do it again to 135 degrees, that's on the upper left. So the highest point of the orbit will now be occurring very near to Morocco. So you see how this twisting motion occurs. The last thing is your mean longitude at epoch. This just declares where you are. If I enter 0, you can see we're now at 0 longitude. That's basically the first of Aries. So here's the Earth. If you draw straight out from the Earth-Sun line, we are around March, which means Aries should be in the Sun, and therefore allow us to prove our fact. Where is Aries? It's a tiny little constellation. There it is. That doesn't seem to be agreeing with me for some reason. Does 7 days really make a difference? Well, at some point Pisces. No, Pisces. I don't know my signs very well. Anyway, the Earth-Sun line, 0 longitude, is defined as the first of Aries. You know, I might be able to get some vectors put on the Earth if I did visual helpers. Was that Alt F9? No, that stops my camera recording. There's like a visual helpers. Let's see, display. There we go. Axes, celestial bodies. There we go. Okay. So the X vector, you can see we're basically almost aligned with this thing. That's the X vector of the Earth, and that's going to point out to the first of Aries. So if I rotate it 90 degrees, that's going to put us around Apoapsis. Oops, other way around. Forgot it's counterclockwise because orbits, the right-hand roll has orbits going counterclockwise. Now if I did it 180 degrees, now we'll be directly opposite of where we stopped. And if I go to 270 degrees, we'll be a little bit past Apoapsis. There you go. And that's how an orbit works. And with that, we're going to go ahead and conclude the scenario and conclude this episode. So hopefully that gives you guys enough information to understand orbits and allows you guys to be able to understand the moon tutorial, which comes up next time. So I will see you guys next time for the trip to the moon. Bye-bye.